Oh, hey. Today we're going to practice more with our skills on eliminating angle parameters when trig comes into the mix and conic sections appear. We're looking back at the same page we were on before, so just a couple examples we left out on page 5 of the parametric packet, and I hope you're ready to go. While you're getting ready, answer me this question. What did the shy pebble wish for? He wished he could be a little bolder, like Boulder. I wonder if you went back to try number 3. We had skipped it the other day because it was so similar to the one right below it and one that we had done on the other page. But just in case you did, check yourself on this or try it now. You're going to get an equation that looks a little something like that. It's an ellipse that's squashed horizontally. It has a center at the origin, and you're coming out 5 horizontally and up and down 3 vertically. And when you start to plug a few points in for theta into the original parametric equation, you're going to get an orientation that I believe is going to be counterclockwise around that ellipse. Now let's get to something that we haven't tried. Can you scroll down? I just made myself some room here, and if you don't have enough room at the bottom of this page, go ahead and use another piece of paper, or if you can, squeeze it into the bottom here. I'm going to call this my new number 6 because I didn't see one on the page that related cotangent and cosecant, and it's good practice for us. So I wrote x equals 2 cotangent of theta, y equals 5 cosecant of theta. Those are your parametric equations in terms of the angle parameter theta, where theta has to stay between pi and 0. All right, let's solve for each trig function. We always start these the same way. So cotangent of theta equals x over 2, whereas cosecant of theta has to equal y over 5. And I got to think back to my Pythagorean identities, right? We know that cosecant squared equals cotangent squared plus 1, squared of theta plus 1, meaning that if you move the trig functions to the same side, you would get this version of the identity. Cosecant squared minus cotangent squared equals 1, and that's what we'll plug into to get some standard form for this conic, whatever it may be. Cosecant squared, so y over 5 squared, y squared over 25, minus x over 2 squared, so x squared over 4 equals 1. And this is looking like a hyperbola. And we've seen a couple hyperbolas before, but we want to be real careful about domain and range restrictions here before we graph the entire hyperbola. Let me move myself out of the way. So you've got a center at the origin, 0, 0. You have 2 vertices up and down 5, so vertices at 0 plus or minus 5. And I wonder which one we care about. Let's also get the asymptotes while we're at it. Asymptotes. Point slope form, you know that the asymptotes go through the origin, 0, 0. So y equals plus or minus the slope, x minus 0 there. Vertically oriented hyperbola means the rise is a and the run is b. So a over b gives you 5 halves as a slope. Now, before we start graphing, because actually I have to change the scale of this too, it's too zoomed in, let's look at the original 2 and decide on domain and or range restrictions. Cotangent is not going to restrict you whatsoever. Cotangent of theta can be any number under the sun, any real number, and x just belongs to the reals. It's the y that we're restricting. We only want the top of this hyperbola or the bottom, because cosecant can't be just any real number in this little range here. Cosecant is the reciprocal of the x value, or of the y value, I should say. And your y values range from 0 all the way up to 1, as high as they can get, and then down to 0 again, with decimals in between. So what that means is cosecant is going to stay greater than or equal to 1. If you flip decimals, you do get numbers that are greater than or equal to 1. So sine's reciprocal is going to have 1 as the lowest thing that it could ever be. Because of that, if you plug 1 in here, y has to stay greater than or equal to 5 times 1. So y has got to be greater than or equal to 5. And it looks like we're only graphing the top half of this hyperbola, the top branch. All right, so here goes. Let me renumber this scale, and I'll count 1, 2, 3, 4, 5. And I'll put a vertex right here. If I'm doing the same thing on this axis, I want to graph this with asymptotes so that their slope is 5 halves. So they're going to come straight through the center, which is 0, 0. And then we're going to go from 0, 0 over 2 up 5, right? So we'll graph it over 2 up 5. We'll graph it roughly like that. Okay. And then we've got another one. Over 2 this way, up 5 that way. And these red lines give you the boundaries for your hyperbola. Let's graph this branch. Whoops. Okay, I went down too far. Have it look like y is only greater than or equal to 5 here. Don't put arrows on the end of it. We have to make a deliberate decision about the orientation using a couple points plugged into the original parametric equation. So easy points that you can think of for theta that fall from 0 to pi, like it's stated originally. So 0, trying to plug in 0, I come up short when I try to get the cotangent of 0. It doesn't exist. I picked pi over 4 as my next value, a nice, easy quadrant 1 value to plug in. 2 times the cotangent of pi over 4 is like saying 2 times 1. And then 5 times the cosecant of pi over 4, I ended up going to a calculator, typing it in, and getting about 7.1. When I tried, what would the next one be? I tried pi over 2, but that didn't get me far either. That gave me an undefined value. So the next one that was good was 3 pi over 4. Still in the range. 3 pi over 4 actually gave you negative 2 for your x, because you would have 2 times negative 1, so negative 2 for the x, and the same y value, 7.1. What that means is you're going, if theta is traveling, as theta increases, you're traveling from this point here, leftward over to that point there. Your arrows need to be pointed, whoops, in the leftward direction. So we'll see how that looks. So we've had a lot of time now to practice with parametric equations, and I hope it hasn't been too bad. I want to just reiterate one more time one of the huge advantages to graphing parametrically over just graphing rectangularly with x and y. Parametric equations show you position, and they show you position at a specific time and a direction in which an object is moving. They also show you a speed. If you trace out different points on a parametric curve and you keep track of where the object is at different time values when t is your parameter, you can differentiate between the speed of two objects traveling along the same curve. The last part to this is a little bit of algebra. It says, could you consider the reverse problem? How can you find a set of parametric equations for a given graph or a given physical description, right? So for examples like these, let's say I wanted to reverse this and start with something I'm really comfortable with. Start with something rectangular, and I want to go backwards. And we've seen this a little bit before. Let's say your parameter is just t equals x. And that is part of your set of parametric equations. A set of parametric equations needs to have two parts. It needs to have a horizontal component, an x equals, and a vertical component, a y equals. And in this case, they gave us what x equals. They want x to equal t. So half of it was just provided for us. What is y? In terms of t, we'll use this original function that we care about. Instead of saying 1 minus x squared, can you make it y equals 1 minus t squared? Believe it or not, that's all you do. This is your set of parametric equations. If we were to graph it now, I mean, we have the advantage that graphing 1 minus x squared is a very simple parabola to graph. It's shifted up 1 unit. I even can show off, because I remember a couple parent points from the graph of y equals x squared. What you've got to do is resist the temptation to put the arrows at the bottom. Your arrows mean something different here parametrically. This thing is either traced out from left to right or it's traced out from right to left. And a couple points plugged into your answer will give you the answer to that 50-50 question of, am I tracing it to the left or am I tracing it to the right? You pick the values. Pick your favorite values to plot. I'm going to go 0 and 1 because they're very easy to plug in. The x's are 0 and 1 because x equals t. And y would be 1 minus 0. And 1 minus 1. You're tracing this thing from 0, 1 over to 1, 0. It looks like we're moving from left to right, and that one's all set. We can answer the same question for this same rectangular graph, and we can make that first parameter whatever we want it to be. Here, they're choosing the random expression, t equals 1 minus x. Fine. That makes it easy to solve for x, so negative x equals t minus 1. And then get x by itself. X equals negative t plus 1. This is half of your set of parametric equations. Now what do we do, right? We've seen this a little bit before. Can you take this back up to the original and find y in terms of t? So instead of y equals 1 minus x squared, do y equals 1 minus negative t plus 1 squared. And you want your answer to be simplified. No parentheses in your final answer. So do the algebra. 1 minus t squared minus double the product plus 1 squared. You'll have 1 minus t squared plus 2t minus 1. And then I'll slide this down here. Y equals, let's get this in order, negative t squared plus 2t, and those 1's should cancel. Here is your set of parametric equations that give you that same graph. I still say sketch the curve just like you would have back in an algebra or a pre-calc class. We are in a pre-calc class, I guess. But I feel like we've moved so far beyond the basics. You've got that same exact curve, the parabola that shifted up a unit, thinking of your parent graph shape. And now decide on your orientation. Pick a couple easy points to plug in. If you guys don't think I'm boring, I'm just going to choose 0 and 1 again. Uncreative of me. So I'll go negative 0 plus 1 gives you a 1. And if I plug 0 in here, I get 0 back. So 1, 0 is the point that's associated with the time t equals 0, since we use that to plug in and get the value. So t equals 0. Happens at 1, 0. Now let's see, is it going left to right or right to left? I plug in a 1, so 1 plugged in here, negative 1 plus 1 gives me 0. And then 1 plugged in here gives you negative 1 squared plus 2 times 1 equals 0, 1. So it looks like this time t equals 1 falls at that vertex of the parabola. So t equals 1 is up here. And the only difference between this curve and that curve, between these two sets of parametric equations, is they're traced out in opposite directions. One is left to right, the other is right to left. And you know what I know is right to left? That I'm drinking this Dr. Pepper. And here's to a good day of solving some parametric equations and getting them graphed. All right, take care.